Okay, this is a long question to solve, but we're going to kind of follow the different steps to go from points in 3 space to collecting direction vectors to then finding normal vectors to the plane, the equation of the plane, and then figuring out the angle between 2 planes. So what I've done is we're going to start with the plane that contains the points A, H, F, sort of that diagonal plane going into the quadrilateral there. All we have are the coordinates, again, in 3 space of point A, H, and F. I've listed them here. So the very first step, if we have to get to the equation of the plane, and we know to do that we need a normal vector to the plane, so that's a vector that's perpendicular to the plane, and we need a point on the plane. Well, we've already got 3 points on the plane, so we're good to go for that. We just need to be able to find the normal vector. So to do that, we can get 2 direction vectors on the plane and then take the cross product of those 2 in order to get the normal vector. So let's first get 2 direction vectors. You can choose any combination of 2 points, so I'm going to do the vector from A to H first. We know to do that we just take the coordinates of H and subtract them from the coordinates and subtract the coordinates of A. So 0 minus 2 for the first coordinate is minus 2, 0 minus 0 is 0, and 0 minus 1 is negative 1. So that's the direction vector AH. We also need a second one, so I'm going to do the direction vector HF. Again, I'll start with the second letter, so that's F, and subtract the coordinates from H. So 2 minus 0 is 2, 3 minus 0 is 3, and 0 minus 0 is 0. So that one's easy. It's just the same coordinates as F. So now we have 2 direction vectors on the plane. Again, we know that we can take the cross product of any 2 direction vectors to get a normal vector that's perpendicular to each of those direction vectors. In other words, if we take the cross product of these 2, we will get the normal vector to the plane that we're interested in. So let's figure out how to do that. So we're going to say AH cross with HF. Now remember, for cross product we eliminate the first column, do 0 minus minus 3 is 3, is the first coordinate of the vector. Then you're going to take the negative by canceling the second column, I should say, and do the diagonals again, and you'll get basically 3 negatives in a row, which ends in negative 2. And then the last one we're going to cover up the third column and do negative 2 times 3 is negative 6, minus 0 is negative 6. Again, cross product should be a pretty familiar formula. So now this is our normal vector to the plane that we're interested in. So to get the equation, again, we're going to use the normal vector and any point on the plane. So to make it easy on ourselves, let's just use the point 0, 0, 0, 0, 0, that's point H. And we'll say the equation of the plane is, we just take our normal vectors and those go in front of each individual variable. So 3x, it's really 3x minus 0, but we don't write the minus 0. Minus 2y minus 0. Again, we won't write the 0, and the reason it's minus 0 is because we're using this normal vector and we're using the coordinates of h right here. And the last part is minus 6z, and we set that equal to 0. So we've got our equation of one plane here. I'm going to follow the exact same steps for the other plane, which is the base of that quadrilateral. Then we'll have 2 equations of the planes, and we can use a simple formula to find the angle between them. Okay, so here we go. I've just added the coordinates of point G up here because we've now included, we want to look at the plane on the base of the quadrilateral, so it contains points E, H, G, and F, but we only ever need 3 points to be able to find the equation of the plane. So I'm not even going to worry about E because the direction vector HF that was on our plane in the on the first plane, and it's also a direction vector on this plane. So I've kept that in here because we're gonna use that just to make our lives easier. So I've added in coordinates G because the other direction vector I'm gonna pick is FG. So to find FG, we start with our second letter, which is G, take the first coordinate and subtract the first coordinate of F. So it's 0 minus 2 is minus 2. 3 minus 3 is 0. 0 minus 0 is 0. So right away we've got our two direction vectors in the plane that we care about. We're going to do the exact same thing and do the cross product of the two to get the normal vector to the plane. So FG cross product with HF. And again, you should be able to follow your cross product rules. Eliminate the first column and you'll do the diagonal. So 0 minus 0 is 0. Eliminate the second and you get negative 0 minus 0, which is still 0. Eliminate the third column and you get negative 6 minus 0, which is negative 6. So this is a really simple normal vector, 0, 0, negative 6, which would make the equation of the plane. Again, we can use this normal vector, and because point H is again in our plane, we can use point H, and this becomes very simple. It's just negative 6z equals 0. So this equation of the plane is even simpler than the other one. Now, in this particular question, we didn't need the full equation of the plane. It could easily ask you for that, but because we're looking for the angle between the two planes, all we really need are those normal vectors. So we're going to take those now and follow the formula for calculating the angle between two planes using their normal vectors. Okay, so here I've rewritten our two normal vectors from the first plane and the second plane, N1 and N2. Let's take a look at our formula that we need for the angle between two planes. It's cos theta, where theta is that angle we care about, and it's N1 dot N2, in other words, the normal vector of the first plane dot product, not multiply, but dot product with the second normal vector, or the normal vector to the second plane, over the magnitude of each of those vectors multiplied to each other. So pretty simple formula. We're going to calculate this right side first and then take the inverse cosine to calculate the angle. So dot product, again, should be very simple to do. You just take first coordinate times first coordinate and take the product of that, add it to the second coordinate times second coordinate, add that to the third coordinate times third coordinate. So this is 3 times 0 is 0, plus negative 2 times 0 is 0, plus negative 6 times negative 6 is 36. So we've got 36 on top. The magnitude, let's do the magnitude of N1 up here. We know the magnitude of any vector is the square root of each coordinate squared and summed together. So 3 squared is 9, plus negative 2 squared is 4, plus negative 6 squared is 36. That is the square root of 49, which is 7. We'll do the same thing with N2 quickly. This one's easy because it's just the square root of 0 plus negative 6 squared is 36, and that is 6. So on the bottom we have 7 times 6, and this gives us 36 over 7 times 6, which is just 6 over 7. So finally, to find theta, we're going to take the inverse cos of 6 over 7, because that was what we said cos theta was. And if you do this in your calculator on degrees, you will get basically spot on 31 degrees, which again is a pretty good sign that we've probably done this right because it becomes a fairly round number. So let's quickly go over those steps again. Take 3 points on the plane you're interested in, get 2 direction vectors, take the cross product of those 2 direction vectors to get your 1 normal vector. So that's a good little trick. 3 points, 2 direction vectors, 1 normal vector. 3, 2, 1. Do that for each of the 2 planes, and then follow this simple formula with those 2 normal vectors to calculate the angle between them. Hopefully this helped. Feel free to reach out with any more questions. Thanks.